Hello everyone, my name is Fauziyyah Mahirah with the student number of 22068211512. In this video, I'm going to tell a little bit about polymer, the classification. We're going to discuss the details in this video. So, what is polymer? If you've already been through 12th grade and you're a science student, I think you're already learning about this. But if you're not, it's alright. You can look around to your spaces. I guess you can notice that there's objects, of course. But specifically, you already know something like plastic bags, bottle plastic, your fake fur jackets, styrofoam, and things like that actually is a polymer. So, what is actually the definition of a polymer? Poly, which means many, and mers, which means parts. It's a Greek language. So basically, polymer is a substance with the molecular structure containing a large amount of monomers, so polymer and monomers, get it? That are repeated and bond together. So it's basically a matter of bonding and interaction between the molecules. So now you guys know that polymer is a molecular structure of some objects. So how do we know if that object is a polymer? Well, we can first compare the polymer with other materials. Let's take an example of metal and ceramics, which are discussed a lot in this kind of class. We could see the comparison from elasticity. Well, we can see that polymer are definitely a lot more elastic than metal and also more elastic than ceramics. And also we can compare the density, density, which means weight per the area. We all know that metal is much more, it's definitely way more than a plastic. For example, steel is much more heavier than a plastic bags. And also we can look for some example like production energy consumption, which means, polymer is definitely a lot cheaper than metal because, plastic bags are way more cheaper than steel. So it's definitely easy to look up the difference between polymer and another material like metals and ceramics. But how do we differentiate the one polymer to another? Because polymer have a lot of types. Disposable spoon is definitely not the same with plastic bags. Or styrofoam is definitely are different with credit cards. And yes, they all are polymers. Then we can get into the classification of polymers. There are lots of types, so bear with me. So for the first classification is the source. There are natural and synthetic and semi-synthetic. Natural is basically from the nature. The example is cotton, protein, DNA, and they're also synthetic and semi-synthetic. Synthetic polymers definitely are a polymer that prepared in the laboratories by artificial means, but semi-synthetic polymers are the polymer that obtained from natural polymers. Also from nature, but it is modified in the lab, so it cannot be degradable in nature, basically. The second is the degradability. So we can see here there are biodegradable and non-biodegradable, and we also differentiate it again with fossil source and natural source. But for biodegradable fossil source, you don't really find it a lot, but it's somewhere. And for the natural source, there are starch, cellulose, etc. And for the non-biodegradable, there are fossil source and natural source. Also, for the example of the fossil source is PE, PPPT, PVC, etc. And for the natural source is bioethylene. This bioethylene is the example of natural source that actually obtained from the nature, but cannot be degradable in the nature. And next, there are structure. There are linear, branch, cross-linking, and network. But there are a lot of types of this, but I'm just gonna mention 4 of it. For the next classification, we got monomer buildings. So what does that mean? It means that this classification showing how the monomers are actually bonds. So there are 2 of it, homopolymers and copolymers. Homopolymers, like its name, consists of identical monomers. So we got some example here. This is polyethylene, polypropylene, and polyphenol chloride. And you can see that there are the N. It shows that it's actually repeating. And yeah, that's that. Next is copolymers, consists of this different monomers. There are homopolymer, alternating, random block, and branch. We already know what the homopolymer means. We could see that the alternating is AB, AB, AB. And for the random, you can see it's random basically. And it's basically just the monomer units are randomly distributed along the polymer chain. And next, it is alternating copolymer. That means that the monomer units are arranged in a regular and alternating sequence along the polymer chains. And there are also block copolymer, which means that the long blocks are segments of one type of monomer and followed by the blocks of another type of monomer. And the last thing, there are graph copolymer, which is in this graph copolymer, one type of monomer forms the main polymer chains, while the other type of monomer branch off as side chains. I also got some photos on how it actually looks. So this is for the linear and acyclic, hybrid, and branch. You can look for the different colors and it contains different monomers. The example of copolymers, there is acrylonitrile, butadiene, and styrene. So for the next one, we got the composition or component of polymer. There are 2, which is organic and inorganic polymer. So organic polymer are composed primarily of carbon atoms bonded to hydrogen, oxygen, nitrogen, and other nonmetals. They are based on carbon-containing compounds, typically like organic molecules, and their backbones consist of C/C, carbon/carbon, or C/H, which means carbon/hydrogen. Example is like plastic, polyethylene, polypropylene, PVC, etc. And another one is inorganic polymers that contains elements other than carbons as the main components. They often involve like metals or metalloid atoms such as silicon, boron, aluminum, and sulfur. The backbones are usually M/O, metal/oxygen, or M/S, metal/sulfur. And the example of it is silicones. Next to another classification is tacticity. So tacticity is described the regularity or the randomness in the placement of the substitution side chains in the polymer chains. There are 3 types of tacticity in polymer: isotactic, syndiotactic, and atactic. In isotactic polymer is where the side chains are all on the same side of the polymer backbones and they have the same like the stereochemical configuration. So basically all the side groups are oriented in the same direction. And for the example is polypropylene and polyethylene. Next is syndiotactic polymer, which means that the side chains alternate regularly in their spatial orientation along the polymer backbones. And syntactic are more alternating and ordered for the arrangement compared to isotactic polymers. The example of syntactic polymer is polypropylene. The last one is atactic polymer. So atactic polymer is where the side chains are randomly distributed along the polymer backbones, so no pattern at all. In atactic polymer, there's no consistency and there are no ordered arrangement in the side group, so this is resulting into the more structure of amorphous. The example of atactic polymer is atactic polypropylene, in which you can find in a certain amorphous thermoplastics. For the last one, we got the functionality of polymer. I got some 5 types in here. The first one is side functional polymer. So side functional polymer is the type of polymer in which the specific functional groups are attached onto the side chains of the polymer backbones. So this side functional polymer have some various of purposes, such as modifying the polymer properties, enabling specific chemical reaction, or providing sites for further chemical modification. So basically, side functional polymer are designed to have enhanced reactivity compared to unfunctionalized polymer. The second one, we have unfunctional polymers. So unfunctional polymers are the type of polymer in which specific functional groups are attached at the ends of the polymer chains. So unfunctional polymers have served also various purposes, like modifying the polymer's properties, facilitating chemical reaction, or enabling specific interaction. So this unfunctional polymer are designed to have enhanced reactivity compared to polymer with functional groups distributed along the chains. The next, we have site-specific functional polymer. So these functional polymer are a specialized type of polymer where functional groups are strategically placed at specific location within the polymer chains. So this level of control allows for the creation of polymer with highly targeted properties and application. So we have telecalic functional polymers. So telecalic functional polymers are the type of polymer that characterized by having functional groups at both ends of each polymer chains, making them N-functional polymers. These functional groups are often identical and are distinct from the repeating units along the polymer backbone. The last one, we got multifunctional polymers that have multiple distinct functional groups incorporated into their chemical structure. But unlike monofunctional polymers, which have only one type of functional groups, multifunctional polymer feature a variety of functional groups, often with different chemical reactivity. So this makes the multifunctional polymers have a wide range of application. So now that you already know a little bit about polymer and its classification, we have to discuss the properties of polymer. So we can look into any properties, but there are 2 main properties that you can look at, which is thermal and mechanical properties. You can define these properties by looking at this one thing that is called molecular weight. So what is molecular weight? Molecular weight, which also known as a molar mass, is a measure of the mass of a molecule in grams per mole. So how does molecular weight affect the properties of the polymer? Now we all know that polymer is the repeating chain of monomers, but even though it's repeated, they aren't the same because the weight isn't the same. Well, ideally, it should be the same, but it is impossible. You can see from this graph, there are a range of molecular weight present in polymer sample. There are something called molecular weight distribution, and they're divided by 2, narrow and broad. So, narrow MWD have the similar or identical molecular weight, not all perfect though, but low on dispersion. So which means they're not really get close to each other. And broad MWD has a wide variety of molecular and are spread out over a broad range. So in here, less dispersity means high regularity, and more dispersity means high randomness. So back to the topic before, how molecular weight affects the thermal and mechanical properties. Let's start with the thermal properties. We can look on two things on the thermal properties, which are the melting point and thermal expansion. So generally, higher molecular weight polymers have higher melting points because the longer chains are require more energy to break their intermolecular bonds. On the opposite side of that, higher molecular weight polymer tend to have lower coefficient of thermal expansion, meaning they expand less when heated. This is because longer polymer chains provide more resistance to thermal expansion. By the way, if you don't know, thermal expansion is a phenomenon where a material's dimension, such as length, area, volume, or density, change in response to change in temperature. So when a material is heated, its particle gains kinetic energy, causing them to move more and on average to be spaced farther apart. This increased spacing between particles leads to an expansion of the material. So the second, there are mechanical properties. So we can look at three things: strength, toughness, and ductility. So in polymers, higher molecular weight often leads to higher tensile strength and stiffness. So longer polymer chains provide more intermolecular entanglements and a greater resistance to deformation. Also, high molecular weight polymers can exhibit improved toughness due to their ability to dissipate energy to chain mobility and entanglement. This is important because it to impact the resistance. The last is ductility. Ductility can vary with molecular weight, so high molecular weight polymer may be less ductile and more brittle, but it also depends on the polymer's specific characteristics. Now that we can actually count how much molecular weight in a polymer, there is something called polydispersity index or PDI that is commonly used in the field of polymer science, so you can quantify the distribution of molecular weights. So you can use this formula that we aren't going to discuss today, but in real life, you can actually have something called gel permeation chromatography. Next, we're going to talk about another thing, which is the polymer and the crystallinity. So how is crystallinity have the correlation between polymer? So if you don't know, basically, so crystallinity is kind of like a measure in like a material that indicates how packed and regularly arranged the atoms. Polymer is actually has the tendency to be semi-crystalline because the arrangement is actually really packed and really tidy, even though it's not perfect. So there are things that actually give the factor on crystallinity in polymer. So the first one is the flexibility. If that polymers is actually have a really high on flexibility, so the first one is flexibility. So the higher is the flexibility, it's actually the lower is the crystalline and the higher of this amorphous. So by the way, amorphous is like kind of the anonyms of the crystalline. It's really random and it's not nicely packed like crystalline. So next, there are cross-linking. In polymer, it usually are covalent cross-linking. So if the linking is high, that means the crystalline is low. The next is branching. So we already talked about the branch. So in polymer, if the branch is more, so it will be less crystalline because the more branch, it means that it's harder to make those crystal. And it's also hard to reach that regularity. So next is tacticity. We also already talked about tacticity. In this segment though, if this polymer is atactous, it will be hard to make the crystalline because atactic is not regular, so it's definitely are more random. For length of chain, so for the length of chains, the longer it is, it will be more amorphous, which is less crystalline. So the last one is intermolecular interaction. So if you guys know, there is something called hydrogen bonding. So it is a type of intermolecular interaction that occurs between the hydrogen atoms attached to an electronegative atom. So actually, polymer with this type of bonding tend to have increased crystallinity because hydrogen bonds can help hold polymer chains in an ordered structure. So strong hydrogen bonding can lead to more tightly packed and ordered crystalline regions. You can actually measure the crystalline in real life. We just use polarized optical microscope, XRD, and DSC. Actually talking about crystallinity in polymer, we cannot talk about TM and TG. So TM is melting point and TG is glass transition temperature. So if you want to look in this graph, so this graph actually showing how you can see the different phases between from amorphous, semi-crystalline, and crystalline, and between those temperature. Melting temperature is actually the temperature which at crystalline polymer transform from a solid state into a molten state or liquid state. So the melting temperature is specific to crystalline polymers and give the information about their degree of crystallinity. So melting temperature is important because you can understand the polymer thermal behavior in the application where melting and solidification of polymer are used, which means in the technique like injection molding, for example. Next is TG, which is glass transition temperature. So TG is a temperature where an amorphous or semi-crystalline polymer transition from a brittle, like glassy state to a rubbery or more flexible state. So this marks the temperature of range over which the polymer undergoes a significant change on its physical properties. So below TG, that means that the polymer is in glassy state, so very high stiffness, breathness, but very low molecular mobility. But above TG, that means that the polymer become extremely flexible with increased molecular mobility and a decrease in stiffness. So TG is very vital because you can use it as a reference point to understand their behavior in some applications. So from understanding what is polymer, understanding what's the classification, the properties, the crystallinity, and like temperature and the formula is really important if you want to understand more about the polymer. So that's all for me. I hope you gained something from this. Thank you so much for watching.